I want to count the ways I get collections, subsets, picking from a group. So let's suppose I'm applying for my club for SHGA, right? What do I need for a club to be recognized by a signal government? An advisor. Club members. The form that I actually have to fill out, I have to have a list of bylaws, a charter, a reason to have the club. I also have to have a board. President, a vice president, secretary, and a treasurer. So, now, if I'm being really pedantic, I also need a Student Hill Senate representative for this club. So I need technically a fifth person, but one of these people could be the person to do that job. These people all need to be different. So 3, 6, 9. There are 13 of you in this room. Congratulations, you're a club. How many ways can I do this? How many ways can I create the board for this club? Again, under the assumption that all 4 of these positions need to be filled by different people. 13 times 12 times 11 times 10. So if I think of the number of choices and I use my multiplication principle, there are 13 people here, but then I can't use the person I chose there. So I have 1 fewer choices. Same thing, same, no, 11 here, 10 there. I can count, really. I just keep subtracting 1 all the way down. And I do it for the 4 people. If it was possible to have somebody serve in 2 spots, I'd have to change the way I counted this, right? But assuming you can only choose 1 person once, this makes sense. On the other hand, if I told everybody in the club to line up, how many ways could I line all of you up? Aha, 13, then 12, then 11, and then I do 13 factorial options. However, I'm going to look at all the possible ways to do this. And then I'm just going to take the first 4 people. Notice, if I just take the first 4 out of that list, isn't that the same thing? Wait a minute. If I take this number and I want to get rid of all of these numbers here, I want to chop those off. But those are being multiplied. Let me think back to Friday.
We could use 13 factorial minus 9 factorial.
But I'm not, well, why would I be dividing?
Multiplying. So if you want to take it away, you divide.
I divide. But let me think back to Friday. Friday, I said if the arrangements are equivalent, then I can divide out. If I really only care about the first 4 people, then it doesn't matter which way these people are arranged, does it? all of those arrangements are equivalent to one another. So I could take the 9 factorial possibilities here, say, hey, those are all equivalent, and really what I need to do is this. But where'd the 9 come from? Oh, I was only choosing 4 people. So everything after the 4th person is equivalent to one another. I can divide those out. I like this idea. We're going to call this a permutation. Out of n items, we have selected r of them. I'm going to write n, pick r, p for permutation. Sometimes you'll see this written as PNR. Different textbooks use different symbols. Same thing. But it then becomes n factorial over n minus r factorial. I have 5 people. I'm going to line them up for photographs. Right? How many ways can I line up all 5 of them? That should be 5 factorial. But I can also think of it as picking 5 out of 5, can't I? So I know that if I want to line up 5 people, I know the number of ways to do that is 5 factorial. But if I think of it as out of 5, select 5, then that should be 5p5. Well, according to this formula, what is 5p5? Remember, we said this was also npr. Using that formula, I'm not allowed to divide by 0. So what the is this? It's 0. So it's not 0. In order for these two things to be the same, 0 factorial has to be equal to 1. Now, it takes a minute for me to try and justify this. But if we think about these as arrangements, right? I want to arrange 5 things, I can do it in 5 factorial ways. I want to arrange 3 things, I can do it in 3 factorial ways. I want to arrange 0 things. How many ways can I do it? Here on the desk in front of me is all of my Olympic gold medals. It's an empty arrangement, but there's the arrangement. There is an arrangement. And that's why the number of ways to arrange no things is 1. Let me stretch this idea a little bit. But before I do that, question. Yes.
There's just 1 factorial and 0 factorial of those equal.
Yep. I have 1 thing. How many ways can I arrange it? There it is. That's it. How many ways can I arrange nothing? 1 way, the empty thing. I'm lining people up to take a picture. So I'm lining up all 5 of my people, right? Let's turn this into a wedding party. I have the bride and the groom and 3 other people. If you're doing wedding pictures, where does the bride and the groom stand? Next to each other. Wouldn't make sense to put the bride at one end and the groom at the other end. That's not a very good auspice for a wedding, is it? So what if we were to take out of this group of 5 and think about the bride and the groom together, then how many ways could I line people up? Now, I'm sure that some of these arrangements will make prettier photographs than others. And if I'm a wedding photographer, then I would probably care more about the optics of the situation than the actual math of the situation. But how many ways can I line the bride and the groom and these three other people up? 4 factorial. Because I can think of the bride and the groom as if they're in a bag, right? They become one object. But that's not exactly true, is it? Why not, Emily? I don't have to, right? I could put them on one end. I can put them anywhere. But at the moment, I said I wasn't considering the optics. I was just considering the alignments, and I want to keep the bride and groom together.
Bride and groom, it's just spots then.
Aha. I wrote it down with the bride on the left and the groom on the right. There's an or in here, isn't there? Bride and the groom, or the groom and the bride. Which means, what do I do when I hear the word or with my numbers? What do I do with my numbers? We did this on Friday. If I add. So I take the 4 factorial where the bride is on the left, and then I add 4 factorial where the groom is on the left, which would be the same as multiplying by 2, right? Because there were 2 options here. Aha, 4 factorial is 24. There are 48 options here. Yes, sir.
Where's the?
Because I had the bride and the groom and 3 guests, right? So now I have the bride and the groom as 1 object and 3 guests. I can think of 4 objects being arranged. There's my set of 4. More questions? Temperature's not right. Anybody want ice cream? I do. I used to love going to Baskin Robbins. How many flavors at Baskin Robbins? Any particular reason you remember that so well? Aha!
Pink. There's the 3 that covers it.
Right? 3, 1. They cheated. They put it in the logo. Sneaky mother. 31 flavors. I want a triple scoop. Again, I'm being adventurous today. They all have to be different flavors. How many ways can you make me a triple scoop cone? 31p3, right? That's a lot of different ice cream cones. But if you are the person scooping my ice cream, and I tell you I want a scoop of vanilla, a scoop of chocolate, and a scoop of cherry, how many ways can you do that? Wait a minute, right? Which one's on the bottom? Which one's in the middle? Which one's on top? Doesn't matter. This counting assumes the order does matter. Because you had 31 choices for the first scoop. And then you couldn't use that flavor again. But the first one's the one on the bottom. I'm building an ice cream cone. And so if I pick the vanilla first, that's on the bottom. But if I told you I wanted a scoop of chocolate, a scoop of strawberry, and a scoop of vanilla, sorry, cherry and vanilla, same three flavors, different order, than the chocolate's on the bottom. That's a different counted arrangement. So when I did this arrangement, the order mattered. And that's another reason I like to think of the P in here for permutation. I am picking my choices one at a time. So I think of it as pick this one, then this one, then this one. Yes, please. I did. So vanilla, chocolate, cherry. They're all different flavors, aren't they? As soon as I chose vanilla, it was no longer an available choice. That's why there are only 30 choices for the next one, right? But if I chose chocolate first, vanilla would still be available, wouldn't it? The number of choices didn't change. Which choices were available changed. I know this is a stupid statement, but I changed my mind. I don't want a cone. Put them in a bowl. Then does it matter what order they go in? 1, 2, 3. They're all just in the bowl, aren't they? They're not on top of each other, not piled. They're just here. What if the order doesn't matter? This number is not going to be right anymore. If the order doesn't matter, then this changes. How does it change? All of a sudden, there are things that are equivalent to each other. Wait a minute. What do I do when things are equivalent to each other? Wait a minute. But that's not when things are equivalent. That's when I've double counted something. And this time I haven't double counted. I counted things way more often than just twice. We said this earlier. Right here, when things are equivalent, what do? I divide. So what do I need to divide by? Say somebody said something. Why 3?
Because there are, for each possible combination, there are 3 ways.
Oh, wait. There are 3 ways? I've got 3 things that I can put in any order I want. How many ways are there to order 3 things? I need to take this number and divide it by the number of ways to arrange those 3 scoops of ice cream. And that's 3 factorial. Now, our formula for 31p3 was 31 factorial divided by 31 minus 3 factorial. And then I'm dividing that by 3 factorial again. Fractions within fractions make my teeth hurt. The hell with the fact that it's about ice cream. I don't want fractions within fractions. That's a cavity. How do I fix that? Take the thing out of the bottom and flip it. Rip it and flip it. 31 factorial, 31 minus 3 factorial, 1 over. Hey, wait a minute. The top's not going to change. The bottom, though, is going to have 2 distinct pieces in it. The arrangements that I threw out because they didn't matter, I wasn't looking at the last 28 flavors, and then the rearrangements that I threw out because they're equivalent ways to rearrange the things I picked. Again, this formula gets used so often, I'm going to steal your word, Seth. I'm going to call this a combination. And I'm going to use the word choose here rather than pick. Choose when the order doesn't matter. And I actually physically think of it as an ice cream scoop, a seed. I'm going to scoop up all 3 of these out of my pile of 31. The order in which they show up in my hand doesn't matter. And then my formula for NCR has that extra R factorial on the bottom, where I took away my equivalent arrangements. Again, we will see other versions of this formula written with different symbols. This last one, a pair of parentheses with the N on top and the R on the bottom, like it was a fraction, but there's no bar in the middle. That's called a binomial coefficient. Because it turns out these show up in algebra class too. Questions? So, how many 3-scoop ice cream cones are there if the order doesn't matter? 3-scoop ice cream cups this time at Baskin-Robbins. Now I can actually cheat, because if I want to do 31C3, (31 factorial is a really big number, isn't it? But the way we figured it out up here was to do 31p3 and then divide by 3 factorial. 31p3 is 31 times 30 times 29. And then I'm dividing by 3 factorial. The bottom is 6. (30 divided by 6 is 5. I just canceled the 6 out. That's a lot easier. 31 factorial is not a small number. I don't want to write that thing down. I don't have to. So I took the 24,000 different ice cream available cones. When I counted all 6 versions with the same flavors as one, I dropped my number down to 4,500. So the real question, when you are looking at your choosings, is does the order matter? But there's also a second question. Can I repeat things? Because both the permutation and combination setups are only usable when things cannot be repeated. If you were allowed to put the same scoop of ice cream in there twice, then it would be 31, 31, 31, right? Very different setup. I'd use the multiplication principle. So differentiating between what I need when is important. Questions? A short diversion on one of my favorite math geeks. I said we called these binomial coefficients, right? What's a binomial? Polynomial with 2 terms. But as a matter of fact, not just any polynomial with 2 terms. I'm going to think of x plus y. Those are my 2 terms. And I'm going to raise it to some power. Ready? When you raise something to the 0th power, what do you get when you raise something to the 0th power? 1. If you raise something to the 1st power, you just get the same thing. Please notice that's 1x and 1y. Algebra time. Now, some of you are going, how the am I supposed to do this? Wait a minute. I'm going to cheat. Can you tell where I got this from? X plus H calc people. You did this throughout all of Calc 1 when we did derivatives. This is the power rule. It's where I did this in the power rule. But now I start to look at this and I start to say, wait a minute, what the hell does this have to do with choosing things? Why do I know it's 3x squared h's? I'm doing x plus y to the 3rd, right? X plus y to the 3rd is x plus y times x plus y times x plus y. And you're going to distribute and multiply all this together, right? But that's really 1 from here plus 1 from here times 1 from here times 1 from here. How many ways can you select one of those to be a y? Out of 3, you're choosing 1. One of them will be a y, the other 2 will be x's. So the way to get this number in front here is to do 3 choose 1. You picked one of them to be a y. The way to get this number here is to do 3 choose 2. You picked 2 of them to be y's. Guess what this one is? 3 choose 0, and this one is 3 choose 3. If you want to do a binomial of any size, x plus y to the n, you're going to start n choose 0, x to the n, y to the 0. Because you chose none of them to be y's. Then you do n choose 1. 1 less n, 1 less x, 1 more y. Then you do n2, x to the n minus 2, y squared. And you just keep going, making the number smaller on the x and bigger on the y. Until you finish it out. These combination numbers show up in my binomials for precisely the same reason, because we're choosing x's and y's, and the order in which we choose them when we multiply them together doesn't freaking matter. So I end up using the combination formula. You ready for the faster way? To fill in the numbers in the middle, you add numbers. This is the 0 row, the 1 row, the 2 row, the 3 row, the 4 row. These are the numbers that show up here every single time. What's the next row? Starts with a 1. Blaise Pascal wrote a book on algebra in which he put forth that this was the easiest way to create this list of numbers. So Blaise Pascal gets credit. It was known about 3.5 centuries before Pascal was born. The first writings we have about this are actually Indian. And they date to about the year 1100, 1200. There's a similar version in Japanese from about the mid 1200s, and there's a version in Chinese. I believe that's the Sea Island Manual by Li Hui in the year 1000. So I don't know why Blaise Pascal gets the credit, but this is called Pascal's formula. And all of these numbers are combination numbers. So if I'm dealing with relatively small combination numbers, this is the way I figure them out. I don't bother to do the multiplication, but I'm not going to write this to the 31st row. So I'm going to cheat. Hit the math button. Whole bunch of stuff up there, right? Look at the last column. NPR and factorial are all right here. So if you want to do 31P3, you don't even have to do the calculation we did here, or 31C3. You can type 31, hit the math button, and say, oh, I wanted to do a combination. There. One step. The problem comes is that comes up here is the limitations of the calculator itself. My calculator is limited in the size of number it can keep track of. So I want to shuffle a deck of cards. How many possible arrangements are there for a standard deck of cards? 52 factorial, 52 math factorial. I think I mentioned this before. That's more than the lifetime of the universe in seconds. If you shuffle a deck of cards, you are on the most part creating something no one else in the universe has ever seen before. Because it would take that many seconds to shuffle one deck of cards a second and see all the possibilities. We are not anywhere near that. But notice what happens if I look at a number not all that much bigger, right? 70 factorial. What happens? The biggest number this calculator can hold is 10 to the 99th power. This number is bigger than that. That's why when I look at 52 factorial, it's got that power of 10 on the end. That's what that E stands for, exponent. As soon as I get bigger than 10 to the 100th, it goes, I can't do 3 digits of exponent. Screw it. That's why I got to go to that big integer calculator stuff online if I need numbers that are that big. 70 factorial is big enough that it overloads this lovely little piece of computing machinery in front of me. I don't know if that got changed in the new update. Anybody have a newer calculator? See 70 factorial work? Does it work on yours? 70 factorial. If it says error, then we're screwed. That's okay. But that's also why I do these calculations in this sort of format and cancel as much as I can so that I reduce the size of the numbers I'm working with rather than trying to do them on the technology. It works on your phone. It's a great thing, but my phone. Yeah, but my phone is not available to me during an exam. Damn. I should see if it works on Desmos's calculator because there's a way to lock your phone into Desmos. Anybody notice anything weird about this triangle arrangement? A couple of unusual things happen. Those numbers are always the numbers of the rows. So that means out of n things, choose one. Well, that's how many things you have, right? Because if there's only one thing, I don't care what order it's in. But the triangle is symmetric. The same numbers are on both sides of the middle. If I were to do the next row, it's always the same. Why? There are proofs done in combinations where you just count the number of things in multiple different ways. Why would this number right here? This is 6C2. This number is 6C4. Why are they the same? What possible reason could there for those to be the same? I don't know if that makes any difference. Then I should have a 3 in there, right? I'm not doing 3 choose anything. Six things. There are 15 different ways for you to pick 2 of those things up without caring about the order, right? 6 choose 2 is 15. But if I pick 2 of them up, isn't that the same as picking the 4 I leave? So if I know the number of ways to take 2 of them away, I know the number of ways to take 4 of them. So the number of ways to choose 2 is the same as the number of ways to choose 4. Up here, the number of ways to choose 2 out of 5 is the same as the number of ways to choose 3 out of 5. So if I pick 2 up, I've left 3 behind. Oh, wait a minute. In general, the number of ways to pick R of them up should be the same as the number of ways to leave the rest of them behind. Now, I've talked about this. Has this actually been a proof? Well, if I write it up carefully, I can make it a proof. But even if I don't write it all that carefully, I can do the algebra. What is the formula? NCR?
Minus R factorial times R.
And NC and minus R is, well, that's N factorial over N minus R factorial, and then N minus R factorial. What happens in this first set of parentheses here? And I get and those are the same damn thing, aren't they? So I can reason it out in a combinatorial fashion and discuss why it should be. But then I can actually prove it algebraically. Questions? Anybody play poker? Well, I expected to see a couple of hands float up. I learned a long time ago, you never play poker with people who smoke at the end of the month. Because they're getting further and further away from the paycheck, they're paying cigarette money, those nicotine addicts are fiends. The lowest possible hand that contains some sort of match is 1 pair. How many ways are there to get 1 pair? And nothing higher. Not 2 pair, not 3 of a kind, not a flush where all of my cards are the same suit, not a straight where they're in some kind of order. Not anything better than 1 pair. A lot of people who play poker will spend an awful lot of time memorizing the number of ways things can occur. My head won't memorize like that, then I'm not doing it. But I can work it out right here. So let me think about this. A pair means I have 2 of the same value. How many values are available to me in a deck of cards? Somebody said it. There are 52 cards. There are only 13 values, right? 4 aces, 4 twos, 4 fives, 4 jacks. Those are the values. So I need to pick one of them to be my pair. There are 13 C1 ways to pick a value. Pick a value, any value. And then I want 2 of the cards from that value, right? So I'm going to take this number and. What do I do when I hear the word and in counting things? That would be in sets. I multiply. Out of the 4 cards in that value, I want you to choose 2 of them. And it doesn't matter what order I get them in, does it? I don't care whether I get the jack, though you said deuces. I don't care if I get the deuce of hearts or the deuce of spades first, as long as I get both of them. But that's only 2 of my cards. I get 5. What about the other 3 cards? Well, it does, because they can't match each other, could they? They all have to be different values. Wait a minute. They all have to be different values from this value, and they all have to be different values from each other. How many other values do I have available to me right now? That's cards, not values. That's way too many. There are only 13 values, right? And I've only chosen 1 of them so far. So there are 12 other values for me to pick from. And I need 3 of them. And the order doesn't matter. And from each of those values, I want 1 of the possible cards. If my pair is a pair of deuces, then my 3 other cards could be any 3 other things: a king, a 5, and a 7. But there are 4 kings available. Which king am I going to get? I don't know, but I need to pick 1 of the 4 kings. Which 7 am I going to get? I don't know, but I need to choose 1 of the 7s. Which 5 am I going to get? I don't know, but I need to choose 1 of the 5. There are 3 of these because there are 3 possible values for me to select. Grab your calculators. Multiply. I'm going to cheat. 5 of these 6 numbers, I already know. When I choose 1, there's only 13 ways to do it. 4C2 was on my triangle. 4C1 was on my triangle. The one I don't know is 12, choose 3. What's 12, choose 3? You own a calculator. Don't try and do this in your head. Well, choose 3. I got a much smaller, 220. 12 times 11 times 10 divided by 3 times 2 times 1. Or use the combination button on the calculator. Multiply all these together, what do you get? How many poker hands are there, period? That would be 52 arranging the whole deck. How many cards do I get in a hand of poker? I only want 5. Do I care about what the other ones are? Do I care about the order in which I got these cards? There are 52 C5 possible hands of poker. That number, 989,860, 2.6 million. If you play poker, the winning hand is most likely a pair. 2 pair would be less likely. 3 of a kind, less likely. How likely is likely? That's what we'll talk about when we get back from break. How likely is likely? By the way, when I bought a deck of cards for playing poker, it came in the very front of the deck with a sheet, or a card-sized sheet with all of these worked out on it. So if you really want to play poker, you don't have to memorize, you don't have to do it, just have to be able to multiply. I'll see you all after break. I hope you have a wonderful Easter. If you came in late and have stuff for me, please bring it up. Otherwise, see you later.